open system availability. What we had looked at before with closed systems, and now very often we have open systems such as turbines, compressors, heat exchangers. And so we've looked at those and we want to be able to do availability analysis of that. So let's look at a general open system. So with a general open system, we'll have a mass flow rate with a total energy entering. It will leave. We could have work produced, power produced, and we could have heat go in. So this is the general form of the first law equation. And so I have Q dot plus M dot E1 is equal to W dot plus M dot E2. And so it's like the energy going in is equal to the energy going out. And now I can rearrange this. So I have W dot is equal to M dot times E1 minus E2 plus Q dot. So what we're interested in, because availability relates to work, or power, what we're interested in is finding the maximum amount that we have. So now let's have the system. Let's look at the system going from state 1 to state 2 and what the functions would look like and how we can find what this reversible work is. So we're interested in, we want to find W dot reversible 1 to 2. This gives us W dot actual 1 to 2. So this is the actual work, our first law analysis. So let's look at a TS diagram that represents this. And we change this lower pressure. A little bit higher. So here we have P1, P2, and we're going from state 1 to state 2. And this first law equation just enables me to find the power if I know the work. So how could we find the reversible work? So the reversible work is found by taking reversible processes between 1 and 2. So we want to find W dot reversible, we're going to follow reversible paths one to 2. So what we're going to do is we're going to go down from 1 to A, and we'll let this be T0. So we're going to go down to a temperature that we know, T0. We're going to go over to B, and then back up to 2. And so what we're going to do is add these works together. So W dot reversible is equal to W dot 1 to A plus W dot A to B plus W dot B to C. So we're going to add these terms together and let's investigate what they are, and we can apply this equation to all of them. So W dot 1 to A is equal to M dot times E1 minus EA plus Q dot 1 to A. Q dot 1 to A is a reversible adiabatic process, so Q is 0. Now we're going to find W dot from A to B, M dot times EA minus EB, plus Q dot A to B. Now here, we know that heat is equal to the area under the curve, so Q dot is equal to T0 times SB minus SA. And then we have W dot B to 2, which is similar to the first one, We have m dot times E2, EB minus E2 plus Q dot B to 2. And again, that's 0 because ds is 0. And so if I add these all together, I'm going to get the following. So we add, we're going to get that W dot reversible is equal to n dot times E1 minus E2. Notice that EB is the same as E2, so the S2 and SB are the same. Minus T0 times S1 minus S2. In E rather, E is equal to H plus B squared over 2 plus GZ. So we have our expression for E, and if I substitute them all in there, so if I substitute all these things in, so we'll have this big expression, and I do it per unit mass, so W dot reversible divided by M dot is going to be equal to psi 2, psi 1 minus psi 2. So this is your open system availability. So if I divide through by m dot, and obviously you need an m dot here too. If I divide through by m dot, we're going to have the following equation. And so I have psi 1 minus psi 2 is equal to H1 minus H2 minus T0 times S1 minus S2 plus V1 squared minus V2 squared over 2,000 plus G times Z2 minus Z1 over 1,000. And we have it over the thousands because we want it in kilojoules as the units in these are in kilojoules. So we've done that. So this gives us the expression for the change of work potential for an open system. And if these two are 0, then it becomes a simple function. So now what we want to do is also have an expression for this where we have the heat availability transfer, the work availability transfer, and the irreversibility. So what we're going to do is combine that and create one of these huge equations such as the one we had for the closed system. So we have the change of the availability of the control volume with respect to time. So this has to do with the volume if it's changing. Normally it's steady state conditions, and this term is 0. So we have 1 minus T0 over Ti times Q dot I minus the work of the control volume minus P0 dV dt. The V of the control volume of time. And I'll explain what these terms mean once I write them all out.